Welcome to this online tutorial. In this tutorial I'm going to cover some basic functions of Microsoft Excel. This is what we're aiming to cover within this session. The session should be around 20 minutes. I'm going to look at how to set up data tables in Excel. Knowing how to do this appropriately will allow you to set data up correctly when you're doing assignments. When you're needing to generate data to put into reports, it's important that it's done in the correct way. So we're going to cover the orientation of the data within Excel, how that should look. We're going to deal with calculating averages and mean values and also standard deviations. Once you have your table of data, we're going to then go through how you would plot that data, which chart type you might choose, whether you might want to consider putting a line of best fit on the chart, whether you might want to consider using the equation for the line, whether you might want to consider looking at other values which you could use to try and help you decide how good your data set is. We're also going to look at how the chart should be labelled in terms of a title and the axes, and also how you can modify the scales on those charts. You'll be provided with the set of data that I've used via StudyNet, so have a go yourselves. Don't sit and watch my version. You'll learn most by doing it yourselves. If we now open up the Excel file, you can see we have a set of data here. This is a theoretical set of data that I've constructed, and the aim of the experiment that I've constructed for you is to measure the concentration of ATP within some samples. Now, in order to do this, I need to use an assay. I'm going to use a commercial assay which measures the optical density at 570 nanometers. So when doing this experiment, if I have some unknown samples that I want to measure the ATP concentration within, I need to generate a set of data, a calibration line that I can use to help me estimate the concentration within those samples. So in order to do this, I make up a stock solution of ATP and I dilute it. As you can see in the table here, I've diluted the sample so that I've got concentrations ranging from no ATP all the way up to 10 millimolar ATP. So by doing this, I have now got samples of known concentration, and if I put those into the assay, I can measure the optical density and therefore plot a graph. From that graph and the data associated with it, I can then estimate the ATP concentration in my unknown sample. As I say, this is a theoretical set of data. You may use a similar approach for other experiments which you're going to do as part of your studies. Now, during this set of experiments, I've taken two readings. We've got here optical density 1, and I've done a replicate called optical density 2. So they're exactly the same samples put through the assay in the same way, but independently of one another. Now, the reason I would do this, obviously, is so that I can create an average of these values and therefore get a more accurate reading for that particular time point, that particular concentration. So, in Excel, I've set the data up going from top down. It's much easier to set data up going down the page in Excel than it is going across the page. If you've got a big set of data, you can very quickly lose it from the field of view if you go across the page. So I'd always encourage you to work from the top down. So the first thing I would want to do then is to create my averages. So within the same data table, I create a column and I'm going to put average optical density, so I'm going to call it average OD, and then the wavelength I'm going to look at is 570 nanometers. Now, if we ever quote a value such as optical density or absorbance, and we say the wavelength that we've used in nanometers, we should represent that as a subscript. So the number, the 570, should be a subscript, so below the rest of the letters that we have associated with it. So if we highlight, so if I click here and I highlight, drag the cursor across to highlight the 570, I go into font and click, and I can select subscript here, and it will subscript the number. So that's how to correctly represent a wavelength for an optical density reading. Now I want to create an average of the data. Okay, so you could calculate the average by adding these two values together and dividing by 2. Do that on a calculator and insert the numbers manually. This is a slower way of doing it. If I click on the cell where I want the average value to appear, I can then begin to type an equation in. So if I type equals, so you'll see the equation starts to appear up here. I need to type in equals average, open the bracket, and Excel tells me what it wants from me next. It wants me to put the bracket, and then it wants me to put the first number that I'm averaging, then a comma, and then the second number, etc. And then I need to close the bracket at the end. Now what I can do is, rather than manually typing in the cell, so this cell here would be C4, rather than type that in, I can just click on that cell. Now if I click on that cell and hold down the cursor and drag across to the second value that I want to create the average from, it selects both values for me. You can see up here we have cell C4, this one here, and cell D4, both within the equation. So if I now click into the equation field at the top, close the bracket, press enter, it's calculated the average value for me. Now obviously I want to fill in the rest of the values in this table. Now I don't have to do that by individually calculating each time the average values using that same equation. What I can do is, if I click back onto, with my left button, if I click onto the first average that I've created, you'll notice in the bottom right hand corner of this square there's a little black box. If I hover my cursor over that, it turns into a black cross. If I press my left button on my keypad and drag down, you'll see that I'm selecting all of those cells, let go of the left button, and all of my average values appear. So that is a quick way to do it. Now, in order to try and demonstrate how variable my data are, I may want to calculate the standard deviation. So I'm going to abbreviate that to STDEV, so standard deviation. Now Excel will calculate this for me as well. You could do it on a calculator, but it's a little bit of a long process. Now again, I click in the first cell that I want to put the standard deviation in, and I click equals, and then I type in STDEV. So equals STDEV, open bracket, and I want to know how much variation there is within each replicate of these two readings. The two readings that make up the average for each concentration. So again, I highlight the two values. Okay, I click on the first one and drag across to the second, close the bracket, and you can see it's calculated in a standard deviation for me, and I can use the same principle then to calculate the standard deviation for all of the data. Now I can either drag that down, or it should, if I double click on that little box, it should fill the table for me. Okay, just like that. So now I have the averages in this column here, and I have the standard deviations in this column here. Now we can't tell much about the data from looking at it in the table. Okay, so we're going to plot a graph. A calibration graph so that we can then try to calculate what this unknown sample is here. Now again, if I've got a separate little set of data away from the main data table, I can still use the equations that I've put in here. I can still use them to calculate the average for this set of data here and the standard deviation as well. If I highlight these two values, so the bottom two values, and I continue dragging down, it will work out the two values associated with these two readings from the unknown sample. Now if Excel comes across any cells where there are no corresponding data, it will just put this error message in here. So we can remove this by pressing delete. Okay, so we have our calibration data in the table and we have our unknown data here. So in order to plot a graph, I need to highlight the columns of data that I want to insert. Now I'm going to insert obviously the concentration of drug, the concentration of ATP that I've used in the experiment, and I'm going to also highlight the average optical density at 570 nanometers. We don't highlight the standard deviations at this stage. So I highlight the first column and then I press Control and I also highlight the averages as well. So both columns are highlighted. Now I then need to insert a chart. So I click on the Insert tab at the top and it brings up the ribbon with all the chart options. Now for this type of graph we would use a scatter plot. Okay, so this will allow us to plot the average data points and then we can decide if we want to use any further analysis to insert a line of best fit or any other type of analysis we may need. We wouldn't use a pie chart or a bar chart or a line chart, it would be a scatter plot. So I click on scatter, okay, and I want the data just to show the data markers only. I don't want the points to be joined up. And I want to see where those data points are, so I would select this first one here. Okay, so I click on the plot that I would like and Excel gives me this particular chart here. Now you can see that Excel does a couple of things automatically. Firstly, it starts putting me a title. And it uses the title generally that's in this cell here. Okay, now I don't want that, so I'm just going to click on it, click on the edge and press delete. I don't want that title, I want to select my own title. It also puts me a legend in here. Now I don't really need this either, so I'm going to delete that. If you had lots of different sets of data, okay, and you were trying to plot several sets of data together, you may want to keep the legend because it will tell you using a different color or a different marker what the different data sets are. But I've only got one set of data, so I don't need that. I'm going to delete it. Okay, so we have our set of data. Okay, now the data is set up correctly. Okay, so the y-axis, so the vertical axis is the y-axis, and on that axis we want the variable that we have measured in the experiment. So in this experiment we measured the average optical density at 570 nanometers. So you can see the scale goes from 0 up to 2. Okay, and that looks about right. So that is the independent. Sorry, that is the dependent variable. The independent variable is the concentration of ATP that we've put into the assay, and this should go along the x-axis. Don't get them the wrong way around. So everything looks okay. We are now going to think about how we're going to label this chart. So if we click on the chart itself with our left button, the Chart Tools option appears at the top of Excel. Now we can do lots of things in here. If we click on the layout, this is where we would go to think about labeling the axes, putting a title on, and those kinds of things, whether we want to adjust the grid lines, etc. So we click on layout, we can see we have all these options here. So the first thing I want to do is put a chart title on. Okay. Now it gives me several options. Firstly, no chart title. If I want it in the middle and over the top of the title, or if I want it above the chart. Well, actually I want it below the chart. A title for a graph should go below the chart. If it's a table, then the title should go above it. Okay, so well, I'm going to click on above the chart and then I'm going to manually move it. Okay, so I'm going to move this down here. If I click on the actual chart itself, I can manually adjust it so this is at the bottom. Now everything should be the same font size. So I'm going to go back to home and I'm going to select size 12 for actually I'm going to select size 11 for everything. Now I can make the chart bigger by clicking in the corner and dragging the chart to being a bigger size. So that's a reasonable size. So I'm now going to think, well, how should I label this title? Well, I'm going to put figure 1, and within the title should contain all the information I need in order to interpret what's happening within this chart. So I'm going to say figure 1, and what have you plotted? Well, I've plotted the average optical density. Now I can adjust where that goes in a moment once I've typed all the text in. So average optical density at 570 nanometers in an adenosine triphosphate assay. Now the units for ATP were millimolar. Okay, so I have a title. Now, so this tells me everything that I've done in that experiment. So it's the average optical density of 570 nanometers in an adenosine triphosphate assay. Now, I need to label my axes. So if I click on layout again at the top, if I click on axis titles, the primary horizontal axis, and I have the primary vertical axis. So we'll do the vertical axis first. So there's various ways in which you can display the actual title itself. I prefer rotated title, so if I click on that, it will bring up a little box for me to type into. So what's on the axis? Okay, well, we have the optical density at 570 nanometers, so OD 570. So I can if I click on the chart, I can move in the axis a little bit to give me a little bit more room. Now, because I've abbreviated here, if we use an abbreviation such as this, we need to put the number, the wavelength we've assayed at, we need to put it as a subscript. So if I click on home and then I click on font, I can select subscript. Now, because I've abbreviated here, I need to tell the reader that that's what I've done. So where I've said here the optical density at 570 nanometers, I would put in brackets here the units OD, well, I would put in brackets the abbreviation OD 570 and then close the brackets, and again I need to subscript here. So click on font, subscript, OK. Now I need to also label my horizontal axis, my x-axis. So again, I click on the chart, I go to layout, axis titles, horizontal axis, and I have it below the title axis. And again, it creates me a little box. It's a bit too cluttered down here, so I'm going to move that up a little bit, and then type in what I have on this axis. Now I have the ATP concentration here in millimolar. So ATP concentration. Okay, so I have my axis labelled, I have a title. Now, if I want to try and estimate unknown samples, then I need to put myself a line of best fit into this particular set of data. If I have a line of best fit, I can then estimate what an unknown might be. Now, how do I put a line of best fit in? Well, I click on the data, and there's an option up here for trend line. Okay, so you can see trend line here. Now I want a linear trend line. Okay, but I'm going to go to more trend line options. Okay, so I'm going to select linear in here, and then I'm going to do another couple of options at the bottom. Now we can choose to set the intercept. So the intercept would be, the intercept is the point at which the line of best fit crosses the y-axis. Now I could set that to 0, and I've decided for this set of data that yes, I do want to do that. For some reason my controls have given me a slightly higher reading than they should. If I don't want to set that at 0, I just I uncheck that box. So actually no, we're not going to set it at 0. I'm going to uncheck that box, and there's some more options there that are of interest to me. Display the equation on the chart. Well, I would like to have a mathematical equation to describe the relationship between my y-axis variable and my x-axis variable. So I'm going to use that. And you've also got a box here, display the r² value on the chart. Now the r² value is called the coefficient of variation. Now this is a percentage value that allows me to assess the linear association between my y-axis variable and my x-axis variable. So if I click OK there, Excel then gives me some data here. It gives me the equation, the mathematical equation of my line, and it also gives me an r² value. Now the r² value will range from 0 up to 1. The closer to 1 it is, the stronger the linear relationship between your y-axis variable and your x-axis variable. So you can see here we have 0.99. Okay, so what this means is that 99% of the variation in optical density at 570 nanometers can be explained by the linear relationship between my x and my y variables. So essentially there is only 0.01% of the variation that can't be explained by the data set that I have. So it's a very good set of data. The closer to a value of 1, the better. Okay, so now I have an equation for the line as well. Okay, now I want to tidy this up. I want to just fill in the grid line down the edge here, the border. So if I double click on that, border color, if I select a solid line, I'm going to make it black and close. Okay, so that's given me a solid line now all the way around my chart. Okay, so what else can I do? Well, if you remember, I have an unknown sample here. Okay, now actually we'll come to the unknown sample in a moment. What I can do actually is I've got my standard deviation measurements here as well. Now it's good to insert these onto a graph because it tells you how much variability there has been in generating each one of these data points. So for every average value we have a corresponding standard deviation. Now because these are set up in the same table, Excel will recognize that these are in the same position on this chart and I can insert them onto the chart so that each one of these data points has a set of standard error bars. How do I do that? Well, I click on the chart. Now again, the layout tab appears at the top here, and on the ribbon you can see there's an option called error bars. Okay, so we want to customize the error bars that we use. So we want, for each data point, we want the standard deviation above and the standard deviation below each data point. I don't want it to be a fixed value. I want to customize it to be exactly these values that I've calculated. So if I click on custom and I click on specify value, a little box appears here. It wants me to put data points, cell points within Excel into these boxes. So if I click on this little Excel symbol here, I can then select all of the standard deviation values that I want. I then click back on the little box here. So that's the positive error, so the error above the line. I then click on the negative error, so that's the error below the line. And I highlight the full data set, not including the unknown sample. This is just for the calibration data. I then click OK and then click close. Now Excel has a little habit of putting in extra error bars occasionally when you don't want them. So it's put in some east to west error bars. I don't want those. I want the error bars that are north to south only. So if I click on the east to west ones and I press delete, I can remove those. So you can see, I mean, they're very small, most of them. You can see that there are error bars here, okay, and they're a different size for each data point. So this looks like a good set of data. The error bars are not large, therefore it looks like a reliable set of data. The two replicates were very close together that went into making each one of these data points. So we have our error bars on there, so the graph is looking pretty good. What I want to do now is estimate my unknown. Now my unknown sample, my sample of microorganism, let's say that I've exposed to an antibiotic, has given me an absorbance value of 0.8. So I could look at this chart and I can see 0.8 here, that's the reading it's given me. I could roughly read across, okay, and down and estimate the value for the ATP concentration. But it's not a very accurate way of doing it. So the way I would actually do it more accurately is to use the equation for the line. Now what this equation tells me is that Y, the absorbance, the optical density value that I have, equals 0.61 multiplied by the ATP concentration plus 0.0445. So the equation for the straight line, y equals mx plus c. Okay. Now, I have a value for y. My y variable, my dependent variable, is the optical density reading. I have that, so I can insert that into this chart, into this equation here. So 0.8 equals 0.1621 multiplied by x is what I'm trying to calculate, plus 0.0445. So if I rearrange this equation, then I can calculate my unknown, which is x. So if I'm rearranging, what I first need to do is take my 0.8. Now I can do this on the Excel chart to show you how to do it, but I would normally just use a calculator. So I can use Excel to calculate for me. So if I type equals 0.8, which is my absorbance reading, my optical density reading, and the first thing we do is subtract. We're trying to get this number over to the other side of this equation. So we subtract, so we do the opposite to the sign that we have here. So we subtract 0.0445. So minus 0.0445. Okay, so that's what is now on the left-hand side of this equation. So 0.8 take away 0.0445 equals this value here, 0.7555. So 0.7555 equals 0.1621 multiplied by x. This has now disappeared because I've taken it to the other side of the equation. Now, because 0.1621 is multiplied by our x variable, and that's what we're trying to calculate, again I have to do the opposite. So I now need to divide by 0.1621. And if I do that, that will move that over to the other side of the equation, leaving my x variable sitting there on its own. So again, I can use Excel here. So equals, I want to divide this value, and then press backslash for divide, and 0.1621. 0.1621. So this now is my x value. So for a value on my y-axis of 0.8, I have a corresponding value of 4.66. So we can cut down the number of significant figures here by using this function. So any value we quote should generally have the same units as those which we've used in the experiment. Okay, so we have got, so for a y-axis value of 0.8, we knew it was roughly between 4 and 6, and it's come up with a value of 4.66 for us. So on the face of it, it looks quite sensible. Now, on our x-axis, we have units of ATP concentration of 2. Now we can change that if we want to. If we click on the axis, double click, it brings up the axis options for us. Now at the moment this is set up so that it goes up to a maximum of 12, which is fine. The major unit is the one that it shows on the graph. You can see that this is 2 at the moment. I'd like to change that to 1. So 2 is the automatic value. If I click onto fixed value and then change this to 1 by highlighting it and inserting a 1, and then click close, I can change that to 1. So now I can see, does my 0.8 look about right for 4.7? Yes, it does. Okay, now if you were plotting the graph by hand, obviously you could draw a point on your y-axis and then rule across to the line and then vertically down to read off your value rather than using your equation for the line. You may want to do both to be able to compare your graph plotted in Excel with a hand-drawn graph. Okay, so that we've analysed this data now. We've looked at how good the data set is. We've got a couple of measures of that. The variability we've got demonstrated for each data point with the standard deviation reading, and we also have our R-squared value, our coefficient of determination as well, which again shows us we have a very good set of data with a very close correlation between our y and our x variables. Okay, now if I want to, I can also vary the y-axis scale if I want to. Again, if I double click on that scale, it brings up the options for me. Again, everything appears automatically to begin with. My major units are 0.2, which is fine, I'm happy with that. But if you wanted to change it, you could click on fixed and then change to whichever value you wanted. Now, if I want to take this and put it into a Word document now, if I'm writing a report, I can right-click on the chart, I can copy it, and if I want to open up a Word document, say I'm into my results section and I want to insert it, I can paste in. Now if I click on paste, there's a couple of options for me. I can paste in as a picture. Now if I paste in as a picture, that essentially freezes all of the data within the chart. So I can adjust the size if I want to, but I can't delete any of the words, I can't change the font size, but it keeps everything in the same position exactly as it was in Excel. Now another option for me when pasting in is I can just paste in normally, okay, without making it a picture. Now if I paste in normally, it keeps it in Word format for me. So if I then want to change things, I want to change the font, so I could change the font size, I can change words, etc. Then I could do that. I could move around the equation for the line if I want to. It allows you to do a bit more to it, but again, it is possible to accidentally change things, so it may be better on some occasions to paste in as a picture. Okay, so that's essentially everything I wanted to show you. We've gone through everything that we decided we wanted to look at in the summary here. Have a go yourselves. The data's up there. If you have any queries, then please give me an email, and I'll be happy to help you.